going to talk about understanding Cassandra from the top of the database all the way down at a conceptual level. I'm going to introduce things in a visual way and then step through them with pictures, so hopefully that helps in understanding. We'll talk about the read path, the write path, all the way from cluster down to data files, and then we'll talk about failure scenarios, what happens when the cluster is in a partially failed state. Okay, these are some pictures. On the left is, if you're not thinking about anything inside, it's just a database. Dive down one level, the database is a cluster. It's composed of multiple machines, each running Cassandra, and they all talk to each other, and together those form what I like to call a ring, also known in Cassandra world as a data center. You can have multiple data centers in a cluster, and each data center has its own copy of the data. Then if you break it down further, if you're talking about a single record, there are a set of nodes that own that record. And I'm going to call those the owning nodes. They're also known as a replica set. And then inside a single node, there's data organized by key space and table in files and directories. The ownership is overlapping, so multiple nodes are responsible for a single record. And at the level of a key space, one of the things that you configure when you configure a key space is to say how many copies of the data you want across the cluster. For all of the examples in this presentation, the replication factor is going to be 3 copies. RF equals 3 is the shorthand for that. Replication factor equals 3. So that's that's halfway down. Now we're going to go farther. Inside a key space there are tables. This is from what things look like on a single node. Inside a key space directory there are table directories, and each one of those table directories holds data files. That's the middle section, df1, df2, df3. I call them data files. Those are also known as SS tables. And inside a data file, there are different parts. We'll zoom in on that in a minute. But before we get into that, you need to understand that there are 3 really important parts of a data file. One is the Bloom filter, which lets Cassandra know easily whether a certain record is stored in that data, whether any part of a record is stored in that data file or not. It will answer for sure not, so that queries can bounce off of that data file fast, or it will answer probably to some level of probability. And so that's number 1. The Bloom filter is pretty small, and I sized the boxes to indicate that. Then there's the key index, and that helps Cassandra know where to seek inside the data file to start looking for the record, the parts of the record. And then there's the data. It's in sorted order, and it's in blocks if you have compression turned on. And Cassandra will scan inside that data portion to look up a record. Once the data file is written, it's immutable, and new cells and tombstones are written to new files, which are then compacted with old files. So it's important to realize that Cassandra does not rewrite data on disk. Like it doesn't, when you do an update, or when you insert new data for a given partition, it doesn't find that partition on disk and then update a part of the disk where that partition is. It writes it to a new place in a new data file. Data files are queried with scatter gather. So when you make a query saying look for partition 1, 2, 3, it's going to, I'll dig into this a little bit later, but it looks in all the data files and then gathers the results. And those results are coalesced. And just so you know, there's an overhead for every table that you create in memory. And you can't get past that overhead. So if you think you want a Cassandra cluster with thousands of tables, that's one thing that you have to think about is, do you have enough RAM on each node to hold that little piece of metadata for those thousands of tables? Okay. I drew those pictures up, and they're going to be part of every single slide from here on. Cluster, ring, owning nodes, single node with key spaces in it, with key space data in it, a key space with tables, a table with data files, and the internal structure of the data file. When the driver connects to the database, it needs a contact point. It doesn't need to know all of the IP addresses of the cluster, it just needs to know 2 or 3. And then it finds out what all the other IP addresses are and connects. The driver keeps knowledge about the nodes while it's up. That knowledge is stale, so if a node goes down, the driver finds out about it a little bit later. And it's updated asynchronously from the driver. You don't, as an application developer, don't have to worry about that. And you can configure the driver to talk directly to a node that owns the piece of data you're querying for. We'll get to that later. All of the slides assume RF equals 3, replication factor equals 3, and the consistency level that we're doing all our queries and writes as are being done at quorum. Quorum means any 2 out of the 3 owning nodes need to respond. Okay, so read. You've got a connection to the database, and now you want to do a read. The driver will issue the query to one of the nodes known as the coordinator node. There isn't a special node that is a coordinator. Any node can act as a coordinator. It just picks one. Depends on your driver settings, but usually it's just round robin. Picks a node and sends the query to it. The coordinator will figure out which nodes own the data that you're asking for or that you're trying to write to, and then it will talk to 2 of those owning nodes. Each owning node does, for a read, does scatter gather on the data files that probably contain the data that you're querying. It checks the. I have a question. Go for it.
The coordinator talks to 2 owning nodes. Is that based on the idea that we're quorum level?
The question is, does the coordinator talk to 2 owning nodes because you're issuing the query at quorum? Yes. If you issued the query at a different consistency level, it might talk to more or fewer. Basically, there's quorum, all, or 1. There are more consistency levels than that, but those are the ones that you can think of. Quorum means 2 out of 3. 1 means it only has to get the result from 1 node, which is not fully consistent. And all means it talks to all 3 nodes, and if any one of them is down, it will fail your read. So all is not a highly available consistency level. Driver then receives, or the results are sent back to the coordinator node, and the results on each node are coalesced, and then those coalesced results are sent back to the coordinator node, and then the coordinator node responds back to the client, to the driver. So now, what does scatter gather look like, and how does it work? On a single node, a read is sent to all of the data files. Some of the data files it bounces off of because the Bloom filter says, the record you're looking for, I don't have any of that data. I know I don't have it. The Bloom filter is a compressed data structure that can answer definitively no or probably. And so it basically tries to read all the data files every time for every read. And the Bloom filter is what prevents further scanning if the record isn't in that data file. The key index makes it so that when let's say the Bloom filter says maybe, the key index, instead of trying to walk the data file, doing like binary search or something like that, the key index will say, this record is approximately like at this location in the data file. Once it has an approximate location from the key index, then Cassandra will go to that location and start scanning. It'll read, the data file is in sorted order, and so if it isn't, it can tell if it's before or after the place that the key index said to go, and it can find it from there. Any questions on that? It's doing all of this in parallel for every data file, for every query. So if you have 10 data files and you query for record 1, 2, 3, it's going to do 10 data file scans in parallel on 10 different threads. And any data files that don't contain that data is an early out. Any data files that probably contain that data, it goes farther, looks through the key index, and then goes and scans the data file, or the data portion. In the data file itself is also a checksum that can detect if there was bit rot in, like the disk twiddled some bits or something. And if it does, it basically gives up, it shuts the node down if it detects a failed disk. Okay, so the coordinator talks to two owning nodes, but do the two owning nodes do the same work? The answer is interesting. One of the owning nodes, the coordinator issues two different kinds of reads. It can issue a read and it can issue a digest read. The read will return the results. The digest read calculates the results, hashes them, and only returns the hash. And the coordinator takes the real results from one node, hashes them in the same way, and compares the two hashes. If those two hashes agree, then it will just return the results it got from the one node. If those two hashes differ, then it says, wait, we have inconsistent results from two of the owning nodes. I need to go make sure that all of the owning nodes agree. So it does this thing called read repair, which instructs all three of those nodes to go get in sync with each other for this one record, and then it returns the results once they're in sync. So a read can, if your data is inconsistent, a read can take longer because it's doing read repair. It's unlikely that your data is inconsistent often, but this can be a source of a longer read. In any case, even if read repair is done, the driver receives the result of the query, the consistent result of the query now that all the nodes have caught up with each other. Okay, we're going to look at data files. Those are some examples of the data file. I'm going to zoom in on one of them so you can see. Those are file listings for a data file. Each data file has several components that are each stored in separate files. I've been talking about data file as if it's a file. It's really not, it's multiple files. Once written, each part of those data files is immutable. The key index is immutable, the Bloom filter is immutable, and the data portion is immutable. Compaction can take two different data files and combine them. It's like a merge sort. Each one of those data files is in sorted order, and it just walks them in order, writing the results to a new data file. If there are parts of a record that supersede another part of a record, it's going to not write both parts to the new data file, it's just going to write the most up-to-date part. So compaction, that's why it's called compaction, because it can throw data away that is no longer needed. Any questions on that? Okay. The data portion is also split into segments if it's compressed. So you don't have to uncompress from the start of the data file, the data portion. You can just seek to one of the start of one of those segments and decompress from there. Compression is default on. So now I'm showing you the listing for one of the data files on one of our clusters. Do you see? Here, let me move this so I can see. Can you see my red dot? It's a little bit hard to see, but there's the data portion. See how much bigger it is than the rest? That is 35 gig, if I'm reading that right. The next biggest part is the index, which is the key index. And that part is 255 meg. That has, it's a sparse, it's like a skip list. So it doesn't have all the keys in it, but it has them in sorted order, and you can easily traverse to the right place in it and find an approximate location for a given key in the data file. Then next is this file called compression info. That has some information about probably some compression dictionaries. I don't know that much about that. The filter.db is where the Bloom filter is stored. The Cassandra does not use the Bloom filter from disk. When it loads the table, when it starts up, it loads that Bloom filter into memory and keeps it in memory, and just accesses it cached in memory. And then there are some miscellaneous files: summary, statistics, table of contents, and the digest, the CRC32 checksum. So if your disk goes bad, and you know, a couple of bits change or a block gets corrupted on your disk, Cassandra doesn't find out about it right away until it tries to access that part of the disk. Once it sees that that disk, that block, or that those bits don't match the checksum anymore, it will usually detect that on either compaction, or when you read the compression, the decompression will fail on a portion of that data section. If it detects that it's likely that the disk went bad, it will shut that server down and say, hey, I'm down, just as if it had thrown out of memory error, or like somebody had killed the Java process. It's a failed node, and you have to recover with the other copies of the data that are on other nodes. Any questions about that? Okay, that is the read path. That's a high-level conceptual introduction to what happens when you do a read. Write is different. When you issue the write to the coordinator node, it's the same kind of thing. There's a coordinator node for a write, but the coordinator for write talks to all of the owning nodes. Even if you issue the write with quorum, it will do the write to all of the owning nodes. However, it will only wait for a certain number of nodes before it acknowledges the write back to the driver. So if you do it at quorum, it will wait for 2 of the owning nodes to say, yes, I accepted the write. If you do the write at consistency level of 1, it will wait for only the first node that acknowledged the write. If you do a consistency level all, it will wait for all 3. If you want lower latency, and you're okay with reduced consistency, you can do it at consistency level 1. It's basically a fire and forget kind of write. There's no guarantee that the write will make it. There's no hard, firm, fast, hard guarantee that the write will make it to all of the nodes. If you write with quorum, it will be a best effort attempt for that third node. Remember that read repair thing? If you write a quorum and read with quorum, then it will patch it up with read repair if it didn't make it to that third node. If you write a quorum and read with one, then you might talk to that third node that didn't get the write, and you'll be surprised that the data that you just wrote isn't there. Okay, any questions on that? Question?
So if one of the nodes fails right, so the recovery that someone does automatically, or do you lose the
The question is, if the write fails to make it to that third node, is there something that Cassandra does automatically to recover that, or do you have to do something in your application? Long answer is there's this process called repair that if you have it running and configured right, it will, in a week and a half or so, finally get around to comparing that one partition and observe that the write didn't make it to the third node and sync it up. The other thing is if you're reading with local quorum, or with quorum, then it will observe the mismatch and patch it up there on the fly during your read. If you're reading at consistency level 1, then you get to see the inconsistent data. Okay, here we go. I got ahead of myself. I wish there was a button that is skip all of the animations and go to the next slide. There is, it's just more complicated. All right. Writes in Cassandra are buffered. So when you say write something and the nodes acknowledge that write, it's sitting in memory first. Even after the writes go to two different places. I meant to create a picture for this, but I ran out of time. There's this one place in Cassandra called the commit log. First of all, you want your writes to be safe. If a node acknowledges that it wrote, it better have saved that write somewhere on disk in case the process crashes. There's a thing called commit log, and when you write something, it gets written to the commit log. Every 10 seconds, the commit log gets synced to disk. So if you do a write and a node fails, that write may not, if it fails within the 10 seconds of that write, the write may not have been written to commit log on that one node. However, the write got written to 3 nodes. The data got written to 3 nodes. All 3 nodes would have to fail within that 10 seconds for your write to be fully lost. And so it's a combination of different owning nodes receiving the write, and every 10 seconds, every one of those nodes is syncing the commit log to disk. That's number one. You want your writes to be safe. If number 2 is the writes get buffered up in memory in a place called the mem table. A mem table is kind of like a data file, but it's just in memory. So if you write to a mem table and then requery that same record before that mem table gets written to disk, it will get read out of the mem table itself, even though it hasn't been written to disk. So the mem table is like an in-memory data file just sitting next to the rest of the data files for that table. But when that mem table fills up, then that mem table gets flushed to a data file on disk. If the process crashes before that mem table flush happens, the commit log is replayed into mem tables, and you're back to the state that you were at as recorded in the commit log. Any questions about mem tables and commit log? I wish I had a picture. Okay, There are multiple levels of caches in Cassandra. There's we already just talked about the mem table. There's also a row cache. When you do a write, any cached data that's sitting in a row cache is invalidated, so that the next time you query, you won't get stale data back from the row cache. If I queried record 1, 2, 3 and got a result back, and then no writes have come in for 1, 2, 3, and then I query 1, 2, 3 again, the result is going to come back out of the row cache. It's not even going to go down. It's not even going to do scatter gather on all the data files, and it's not going to hit the disk or try to scan for the data. It's just going to come out of row cache. That assumes you have row cache turned on for that particular table that you're querying. That's not the default. But if you do a write for record 1, 2, 3, the cached value of the row 1, 2, 3, the partition 1, 2, 3 is discarded from the row cache, and you have to go do a read the next time you read record 1, 2, 3. Mem table queries. If you do a write and then a read of the same data, it's just going to come out of the mem table, which is a in-memory data structure. It's pretty fast. The key cache is not really a cache that has to be invalidated because it's an immutable part of the data file. Once it's written, the key cache doesn't get invalidated on write. The only time that the key cache gets invalidated is when two data files get compacted together, then a new key cache is computed for those two. The other thing that's important to understand is that instead of going to some round robin, luck of the draw coordinator, you can configure your driver to be token aware. What that means is the driver predetermines which nodes own the data that you're querying for, and it will talk to one of those owning nodes directly. So here's how that works. Instead of going to some arbitrary coordinator in the ring, it just talks to one of the owning nodes, skipping that whole coordinator step. And owning a node that knows it owns the data reads the results. It issues one of those digest reads against another node, and does the same logic. It just skips all of the one-hop processing that a non-owning coordinator would do. If you just do round-robin coordinator, then you get, on the luck of the draw, sometimes you get a node that owns the data, and so it's cheap. Sometimes you get a node that doesn't own the data, so it has to hop over to one of the owning nodes, and that costs an extra couple milliseconds of latency. Sometimes it's not even that much, but you do end up paying garbage collection on that non-owning coordinator because it has objects on its heap that were just there because it was trying to return the response back from one of the owning nodes. If you configure your driver to be token aware, then you skip that extra garbage collection that happens on the non-owning coordinators. Okay, where are we at on time? 12:30, so we've got plenty of time for failure scenarios. Okay, so let's say one of the nodes is down. It's dead. The Java process died, it got a seg fault, whatever. AWS, there was a bad piece of hardware, and the VM is no longer responding. One of your nodes is dead. The way that Cassandra detects dead nodes is it's running this protocol called gossip. Every node is saying to every other node, hey, I was able to talk to node A, it's up. Node B, I haven't got a response back from node B in a while. And it's this token that goes around all of those nodes. Eventually, with a long enough time happening with node B not responding, it gets marked down on all of the nodes. Once all of the nodes know that a certain node is down, then it will no longer even try to talk to it, except for a background process that's going to detect when it comes back up again. I think that's also part of gossip, but if the responses get so slow that gossip it's basically marked down because it's effectively down because the responses are so slow. Once a node is marked down, then the number 1, that is echoed, that information is echoed late out to the driver, and so the driver won't even try talking to the down nodes, and the coordinators won't even try talking to the down nodes. So one node is down, it will talk to the other 2 owning nodes if you issue a read at quorum. If a node is newly dead, like it's in a big garbage collection and it's about to die, or it hasn't responded in like 5 seconds, if one of those nodes is like in a non-responsive state, the coordinator will talk to 2 of them, and if it doesn't come back fast enough from one of them, it will give up on that one and start talking to the other one. That's something that happens behind the scene on the server side. You don't even have to think about it. That's called speculative retry. So it's either known to be dead, and so I don't even try talking to it, or it's in the process of going down or in a momentary unhealthy state. And speculative retry makes it so you don't have to sit there and wait for 5 seconds for garbage collection before a query comes back. Okay, so what if there are more than one of the owning nodes that are dead? If you issue a query, it's going to talk to the owning nodes. It's going to notice that 2 of the nodes are down because you asked for quorum. It can't get 2 out of 3, and so it says, hey, I'm not even going to bother talking to the other node. I'm just going to say, sorry, you can't get this query is not satisfiable right now. So think about the impact surface of 2 nodes in a 20-node cluster. How much of the data, percentage-wise, is going to be inaccessible if 2 nodes are down in a 20-node cluster? And think about it like this. There's 3 racks, they're called in Cassandra, and every rack has a full copy of the data. I didn't draw the racks up here. If the 2 nodes are down in one rack, no problem. You can always talk to the other 2 owning nodes, and those other 2 racks have a full copy of the data, no big deal. If there are 2 nodes down across 2 different racks, though, there are some parts of your data that are not able to be addressed at quorum. When that happens, then a lot of your queries just go through because those 2 nodes don't own the data that you want anyway, so you get into this partially failed state. In a 20-node cluster, I don't know the math, but it's like, low single-digit percentage of the number of queries that are going to fail. Sometimes I've operated clusters where that has been the case. There were 2 nodes that were down, but the site basically was up because it's a long story, but we used to run lower consistency queries where it didn't really matter if 2 nodes were down because you could always talk to the other one. But we were more okay with stale data earlier on. Now we've gone to quorum. So if you're okay with reduced consistency, use consistency level 1, and it won't matter if 2 of the nodes are down.
Can you fail over to consistency level 1 if 2 is down? Start try 2, and if it doesn't work, then go in line?
The question is, can you fail over to consistency level 1 if you observe quorum failures at quorum? Yes, that's possible. You could detect that in your application code, do that, if you're okay with the reduced consistency. It may have been that one that's still up was the 3rd node that didn't get a recent write, and so if you fail over to consistency level 1, you may get stale data. Okay, so what happens when a single node is down and you're trying to write? The driver talks to the coordinator talks to all the owning nodes. If one node is known to be down, the coordinator will store a thing called a hint. And that is, it stores the data that was written in a special file that is buffered, sitting there waiting for that node to come back up. When the node comes back up, that coordinator finds out about it, replays the missed write, and that node is fully caught up. When the node comes back up, it does not, it doesn't wait for all those hints to be replayed before it starts accepting traffic again. It'll start accepting reads and it'll start accepting writes. In that case, where you're trying to read one of those records, if you read at quorum, it's relying on one of those other rows to generate a mismatch, a digest mismatch, and catch it back up before the hints come back. So just be aware that when a node comes back up, it starts serving reads immediately. It doesn't wait until hints get streamed back to it. If one of the nodes, like if you do a write and the node that is dead is newly dead and it isn't known dead, then the coordinator will just give up. The write will never make it to that node, and it's up to read repair or that cluster repair to patch it up and get the data to that third node. So there's a time window between when Gossip detects a node down and when it's no longer accepting writes, when those writes are just kind of dropped. That's called a dropped mutation. Okay, so what if multiple nodes are down and a write happens? The driver talks to the coordinator talks to all owning nodes. If you can't get quorum for write and the nodes are known down, the coordinator won't even bother trying to apply that write. It'll just give up and say, sorry, I couldn't get quorum for this write. I'm not even going to try to write it anywhere. Fail. If they were up and they were newly down, you know, that point where it's 100 milliseconds after it's in the stop the world garbage collection, and two of the owning nodes go into that garbage collecting state, the coordinator will write to the third node, eventually fail on those two nodes that are newly down, and fail and say, hey, I couldn't do this right. Sorry. It's the same answer. It says, the write, I wasn't able to get quorum. However, it's a different result. In one case, if it was known down, the data never got written to that third node. In the other case, if the nodes weren't known down, then the data got written to that third node and it's sitting there and it will eventually get replicated to the other three nodes, but you got an error on your write. If you want to use Cassandra, you have to have a data model that's okay dealing with that scenario where there's data that isn't acknowledged everywhere, but that still got written. If you're okay with reduced consistency, you can just do your writes at CL1, consistency level 1. And like if you're just collecting data, Cassandra is a really good, highly available data collector. So you can have two nodes down and still accept a bunch of writes. It comes with a little bit of risk. So that one node is the only place where it's sitting in commit log. You lose those two nodes, now you're down to a single point of failure for your writes. If the kind of data that you're collecting, like sensor data or something like that, where one dropped sample isn't a big deal, that's an okay consistency level to do your writes at. If you need higher availability for your writes, you can turn off the token-aware driver. And if the two nodes that own it are down, it won't send you to the bad nodes. It will talk to some other coordinator which will queue it up, hint it, and move on with life. Any questions about that one? This is the most complicated one. One question.
If you have token-aware driver on,
Yes.
and the node that owns it, one of the nodes that owns it is down,
Yes.
it automatically just loaded a different coordinator.
So the question is, if you have token-aware client on and two of the nodes that own the data are down, why wouldn't the driver go to use a different coordinator or go to the node that's up? The answer is if they've been down long enough and the driver has found out that they're down, that's exactly what it would do. If the driver hasn't found out that they're down yet, it will take a little bit longer for it to figure that out. Did that answer your question? Okay. Any other questions?
So if a node goes down hard, say fault or something.
Yep.
Way to automatically bring it up, is that take manual intervention?
The question is, if the node goes down hard, like a seg fault or something, does it come back up automatically, or does it require operator intervention? Did I get that question right? By default, it stays down, and it requires an operator to start it back up. You can configure an external process to watch for down nodes and restart them, write a script or something like that. It's usually stable enough that you don't have down nodes without good reason, and it's useful to be able to troubleshoot what happened before you bring it up in a weird state. That's my experience. Any other question? Okay, that covers it. Any other question you've held till the end? Anybody who knows Cassandra? Okay, I have a question.
Yeah, I was wondering about failures that are caused outside the system, like fire, earthquake, something like that. Are these nodes together someplace physically, or are they separated far enough apart that disaster like that?
So the question is, how do you deal with disasters like earthquake or fire or data center failure or large-scale failures? One way that we've done it on a database that I work on is we have a cluster with 2 different rings, one of which is serving application traffic, and another one of which is sitting across the country from it. And we configured the driver to just talk to this ring that was this Cassandra data center that was sitting next to the application, and we made it so that all of its queries could be satisfied locally right there. Any writes that are happening are getting replicated with the caveats of, a downlink or not able to talk to those nodes over to that across the country data center or ring, and we're doing our backups over there.
We should point out we're in different AZs also, right? So
Yep.
it is a different building with different fire system.
Another comment is, we have the cluster that's configured over here that the application is talking to in 3 different racks, Cassandra racks. But we've put each Cassandra rack in a different AWS availability zone. So an availability zone has an isolated network and an isolated fire system, and it's in a different building. So if there's a problem that's isolated to one specific AWS availability zone, then we will still have 2 copies of the data up and responding, and hopefully won't have a major outage. One more question.
How do you guys handle for that backup in your secondary ring, how do you guys handle when something happens on that to make sure that backup is in a stable state, or it can be in a recoverable state for your primary application?
So the question is, how do you handle when that secondary ring, that other data center that's sitting across the country is in an unrecoverable state? Did I?
Or data gets lost in transition.
Oh, okay, so data is dropped, like there are writes that happen over here from the application that don't end up making it over there. That's actually a topic that we're actively working on.
Repair.
Hints pile up.
Hints pile up if the network goes down, and we're constantly running Cassandra cluster repair that fixes things up over days, but we don't have a full solution for every last write making it across in the last 15 minutes yet.
So then are there separate coordinators or separate drivers then, one for reading the only read? that?
Yes.
And then a separate write driver that's writing to both, so it knows the pilot difference?
The question is, how does it work when the application writes over here? Do you have to do a separate driver that knows about that other cluster? If they're in, or that other ring, that other data center over here, the answer to that is the way we have it configured, they're all part of the same cluster. We configured the driver so that it only connects to those local nodes, though. There is no network path between the application and these other nodes, so they can't even talk to it. What we're planning on, I'll go just a little bit farther, what we're planning on doing to ensure at a higher level of confidence that the writes that happen over, that are close to the app, eventually make it out there as soon as possible, is we write at quorum over a thing called local quorum over here, which means that you don't have to guarantee that it makes it across the country, but we're going to do something that asynchronously reads at all, which makes it so that read repair syncs the clusters faster than the cluster repair would across the country. And then if your link goes down, then you're stale for however long the link is down. But when the link comes back up, those things get queued up, those background checks get queued up, and then they go and read repair recovers faster than cluster repair would. Any other questions?
On a read repair, when you have to go to that third node for the read,
Yes.
the process simply, if two of them match, because of that fixes the third, or is it more complicated?
I don't know exactly. The question was when read repair happens and asks to talk to that third node, how does that work? I don't know exactly how it works. My understanding is it tells the three nodes, hey, for this partition, I want you to send what you have to every other node that owns it. And I don't know exactly the details of how it works, but it basically syncs everything that node A has with node B and C, and B sends everything that it has to node A and C sends everything that it has to nodes A and B. Once that's done, then it reads from two of those nodes. That's my understanding. I might be wrong on that. Any other question? Okay, thanks for coming.